Okay, so let's do another example with radioactive decay. Now, in this one, we're not going to be working with a substance that is known. I just made some numbers up, and we just know that it's going to be decaying um, exponentially. So what we have here is that we have gone from 230 grams to 192 grams in the span of 5 hours. And so the question here is to find the rate of decay, find our K, and then find our half-life. Well, we see that in 5 hours, we have not even lost half of that. So we know the half-life has to be more than 5 hours. So let's really work on that and see what we come up with. So if we start with that basic form, that the amount based on time is equal to the initial amount times e to the kt, let's plug in what we know. So we know the initial amount because that's this. We know that at a certain value of time, t equals 5, we have this right here, the amount after 5 years. So we have a of t. We just don't know k. So we plug in what we know, and we figure it out. So we end up with 192 after starting with 230 grams, e to the k times 5. I bet you know where we're going to go from here. Since the variable that we want is in the power, we know that we're going to have to take the log of both sides at some point, but not yet. We have to first get rid of that coefficient out front. And so now we have 192 equal, or over 230 equals e to the 5k. Now we apply the natural log. Things get super nice for us on the right side. And I'm just going to go and write that on the left. So this piece becomes 5k equals the natural log of, yes, I know it simplifies, but I'm not going to spend the time doing it because it's going to go in the calculator anyway. So the k, the exact value, is going to equal the natural log of 192 over 230, all divided by 5. So let's type that into the calculator and see what we come up with. We have the natural log of 192 divided by 230. Make sure you close your parentheses, and then divide by 5. So this is approximately negative 0.0361. Let's go to 4 decimal places. I think that'll be good. So this is my rate of decay. So in other words, about a negative 3.61%. Okay. But here, this is your main value that you want to use for k. We're just trying to turn it into percent so we can maybe understand it a little bit better. All right, the next part is saying what's the half-life? And again, using that formula that I've shown you before, the natural log of 1/2 is equal to k times t. In this problem, natural log of 1/2 is a constant. K is the constant that we just found right above. And we just need to find t. So t equals the natural log of 1/2 divided by k. So our time for the half-life is the natural log of 1/2 divided by negative 0.0361. Now again, we said that our half-life should be a little bit more than 5 days. So let's see what we have here. So natural log of 1/2 divided by negative 0.0361. And so it tells me this is about 19.2, not days, hours. Man, gotta pay attention to what it says. Yep, so yeah, 5 hours. It said hours. I'm not sure where I got the days from. Pardon me, please. So this is our half-life. Okay, now the next part says how much of the substance remains after 1 day. So before I do that, let's make sure we understand that our form is this guy right here, except we know in our k and our t is going to be the variable. So the basic format for this, our initial amount is 230. My k is negative 0.0361. So then my function that I can use for anything else in this problem is 230 e to the negative 0.0361 t. So I can use that for anything. The question is, how much remains after 1 day? So after 1 day, pay attention. 1 day is 24 hours. So we have to make that conversion because our t here is being measured in hours, not days. We found the half-life to be 19.2. That was hours, not days. So 24 hours is going to be a little bit more than one half-life. So one half-life would turn the 230 into 115. So this guy's going to be less, I would imagine less than 100. But let's go to the calculator and let it do the dirty work. So we need to find a of 24. And I'm going to do this a little bit differently. So I have 230 e to the negative 0.0361 x. For my window, we're going to go from, let's say, 0 to, let's see, 19 hours is one half-life. Now, let's go to 100. With a scale of 10, my y min is going to be 0 because you can't get less than that. The y max is 230 because that's what we start with. Y scale is 10. Let's see what the graph looks like. Okay, doing exactly what we thought it would do. Now we're going to use this graph to do some checking here. So let's trace. Now the problem that we're doing right now is wanting to know what is it when it's 24 hours. Yeah, 24 hours. So it tells me that in 24 hours, we have approximately 96.7 grams remaining. Let's check the half-life here. 19.2 should give me half of 230, so 115. Yeah, I mean, again, it's not exactly 115, but it's close enough. All right. And let's see, after 5 hours, the original problem said we had 192 grams left. So yes, everything is matching up here. Now the last part here says, when will there be only 20 grams remaining? So we could definitely trace along here and see when is it going to be 20. We could go to the table. There's going to be a lot of clicking to get down to where it says 20. Or, like we've been doing, let's say 20 for this, for the second equation. Now, each of these tick marks is 10 hours. So 1, 2, 3, 4, 5, 6, almost 7. So I'd say like 68 or 69 hours. Let's calculate this. Intersection. First graph, second graph, guess, good enough. And so we see here that in about 67.7 hours, only 20 grams will remain. Now, that's using the calculator to do the work, right? But suppose we don't have use of a graphing calculator where we can do the intersection. That means that we would need to take our function. So again, let's remember our function. For this particular example, 230 e to the negative 0.0361 t. And that's the thing to understand. It's just for this example that has this starting value and that rate. Okay. We want to know when will this, what does that equal 20? Well, you solve it just like we've done everything else. divide by that leading coefficient. Those guys go away. We have e to negative 0.0361t. And then we apply the natural log to both sides. So negative 0.0361t. And we divide both sides by that coefficient. So over negative 0.0361. So this is the algebra. Again, we're going to have to use a calculator, though, in order to do the actual calculation. So natural log of 2 over 23. Oh, excuse you. 2. Well, if I had tried hitting enter, it would have given me a syntax error. It would have said, I don't know what you're doing. Oh, look, it gives me the same thing, 67.655, and we said 67.7 when we rounded to the nearest tenth. So yeah, still the same thing. That's cool. It's nice to see everything working out so splendidly.